Hello students, welcome to EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module entitled Group Representation from the paper Mathematical Physics. So student, let us see what we are going to learn in this module. Well, in this module, we will learn about group representations, which play the most important role in studying the consequences of symmetry operations in physical applications. We will learn about equivalent representations. More importantly, we will learn about reducible and irreducible representations, and finally, we will learn to construct representations of finite group. Group representation plays a most important role in deducing the consequences of symmetry operations in physical applications. Representation of a group is in some way a method of realizing the group operations in a way other than the original definition of the group. So you have the original definition of the group, then you find a representation which realizes the same group of operations as the group elements. In quantum physics, for example, we are interested in studying the consequences of group of transformations, rotations, etc., on the states of the physical system. The states of the physical system are represented by vectors in a suitable Hilbert space in quantum mechanics, as all of you know. Realization of group operations by matrices is of particular interest in most physical applications. The multiplication on matrices can then be naturally associated with group multiplication. We will now define what is meant by a representation. Given a group G whose elements are I goes from 1 to n, so the group has n elements. For each AI belonging to G, suppose there is a n by n matrix D of AI which satisfy the same multiplication laws as the group element AI. That is, if AI Aj is equal to Ak, then it implies that the product of the matrix DAI with the matrix Daj is equal to the matrix D of Ak. If this is satisfied, then the D's form a n-dimensional representation of the group G. In fact, it's an n-dimensional matrix representation of the group G. In other words, the correspondence or the mapping going from the element AI to the matrix D of AI is a homomorphism. If this homomorphism is also one-to-one isomorphism, then the representation is said to be faithful. The identity element of the matrix is represented by a unit matrix, and the matrix which represents the inverse of an element is equal to inverse of the matrix representing the element. That is, DAI is equal to DEAI by the law of multiplication of the group, which is equal to DAI because EAI is equal to AI. Therefore, D of E must be equal to a unit matrix. DAI inverse by the group multiplication is equal to D of AI inverse, but AI inverse is equal to the identity element. So this is equal to the matrix corresponding to the identity element, which is the unit matrix. That is the inverse of that is the matrix of the inverse of a element is equal to inverse of the matrix. There are certain corollaries which follow from this. If D1A and D2A are both matrix representation of the group G of A. In fact, in general, given a group G, we can have more than one matrix representation. So let's consider two matrix representation D1 and D2. Then if we define a matrix D3 as matrix formed from the matrix D1 and D2 in the following way, this first element is D1 of A in the first row, second element in the first row is 0, first element in the second row is 0, and the second element in the second row is D2A. Then D3A can be denoted by a direct sum, that is D3A is equal to D1A plus D2A. And this also forms a representation. Proof. For any two elements A1 and A2 belonging to the group G, then matrix representation of A1, A2, namely D3A1, D3A2 is equal to the product of these two matrices which are shown in the slide. When you multiply the two matrices together, we get a matrix whose first row consists of the product of two matrices D1A1 into D1 of A2, and the other diagonal element of this matrix consists of the matrix D2A1 multiplied by D2A2. But from the rule of group multiplication, the first diagonal element is D1 of A1A2 and the second diagonal element is D2 of A1A2, and A1A2 is equal to A3, therefore is nothing but D3 A1A2. So we have shown that the direct sum of representations is also a representation. In general, we can construct all representations by taking the direct sum of other representation. That is, if D1, D2, D3, Dn, etc. are the representations of the matrix representation of the group, then the matrix DA formed by taking the direct sum of all these matrices is also a representation. So the question we should be asking first is, are there representations that cannot be expressed as direct sum of other representations? There are indeed such representations which are called irreducible representation. That is, the irreducible representation cannot be expressed as a direct sum of some other representation. Be that so, the two questions immediately come to the mind. Number one, are the irreducible representation important? And then, how do we know whether a representation is irreducible or not? Well, the answer to the first question is irreducible representations are important because they are the building blocks and all other representations can be built from them. For example, in particle physics, irreducible representations are the states of fundamental particles, and reducible representation mix these states. Now, how to know whether a representation is reducible or irreducible? Well, there exist in the literature theorems and lemmas which tell us whether a representation is reducible or not. We are going to learn about these theorems and lemmas subsequently. So first let us define what we mean by reducible and irreducible representations. A representation D of a group G is called irreducible if it is defined on a vector space V of D which has no non-trivial invariant subspace. If there exists a non-trivial invariant subspace in the vector space V on which this representation D is defined, then the representation is not irreducible. If there exists no such subspace, otherwise, then the representation is reducible. This means that for a reducible representation, linear operators corresponding to group elements will leave some smaller vector space invariant. The vector space view of D, which is used to generate the representation D of G, has the following property. So, there are certain properties which are satisfied by the vector space V, which has been used to generate representations of G. What are these properties? For every element A of G, and there exists a vector V belonging to the vector space such that A operating on V also belongs to the same vector space. The vector space V is closed under the group operation. When is it closed? It's closed if the operation of any element of G on any vector V which belongs to this vector space does not take us outside this vector space. So, a vector space S is a subspace of V, written as S subspace of V, if every vector of S is contained in V, and is called a proper subspace if S does not exhaust the space V. V is a subspace of V, but is not a proper subspace. A vector subspace S, which is closed under G, may possess a proper subspace H, which is also invariant under G. In such a case, S is said to be an invariant subspace of V under G, and the space V is said to be reducible under G, otherwise it is not. Having discussed what is meant by reducible and irreducible representations, we will now show that if the representation D is reducible on the vector space V, then there exists a subspace S which is invariant under G. That is, if a matrix is reducible, then there exists a subspace which is invariant under G, which means that any vector V belonging to this vector space V can be decomposed in the block form S and SC tilde, where the vectors S belong to vector space S and S tilde belongs to the complement of the vector space S, that is S tilde. Representation matrix can then be written as D of A is equal to D1 of A, D2A, D3A, D4A in the form of a 2 by 2 matrix. These themselves are matrices acting on the space S and S tilde. For the space S to be invariant under group operation means that D3 AI is equal to 0 for all AI belonging to the group G. That is, the matrices DAI are all of the upper triangular form. That is, the matrix DAI is in the upper triangular form with all the other elements in the matrix being 0. That is, the way it is written in the slide is D1 AI, D2 AI, 0 and D3 AI for all AI belonging to G. A representation is said to be completely reducible if all matrices in the representation DAI can be simultaneously brought into the block diagonal form by the same similarity transformation U. That is, if there exists a matrix U such that U DAIU inverse is in the form of a block diagonal matrix, that is D1 AI 0 0 D2 AI for all AI belonging to the group G. That is, the space complement to S is also invariant under the group operation. This happens if representation matrices are unitary. Theorem: any unitary reducible representation is completely reducible. Let us assume that a scalar product is defined between two vectors u and v in the vector space V. The scalar product between two vectors is defined as u comma v, which is equivalent to u dagger v. We can choose the complement space SC tilde to be normal to the space S. What does it mean? It means that the scalar product of U and V is equal to 0 if U belongs to S and V belongs to SC tilde. That is, there are two spaces, the space S and the orthogonal space SC. A vector belonging to S is orthogonal to a vector belonging to the complementary space. A scalar product is invariant. Now, it's easy to see that scalar product is invariant under the unitary transformation. Consider the unitary transformation which takes the vector U to U prime. So, U prime is equal to a matrix U operating on the vector U, and V prime is the unitary matrix U acting on the vector V. Then U prime, V prime scalar product is equal to U prime dagger, which is defined as U prime dagger V prime, which is equal to U dagger UV is equal to U dagger V is equal to UV. That is, the scalar product is invariant under the unitary transformation. This is a result which is known from your algebra class. Thus, the scalar product of two orthogonal vectors UV is equal to 0 implies the scalar product of the transformed vectors dAIU and dA2V is also equal to 0. Thus, if dAIU belongs to the space S, then dAIV belongs to the complementary space S, which implies that complementary space is also invariant under the group operation. In physical application, we mostly deal with unity representations and they are completely reducible. Since unitary operators preserve the scalar product of a vector space, unity representations simplify the group theory applications. An important theorem is that every representation can be made unitary by a suitable similarity transformation. The proof is straightforward. Let D of AR be a representation, that is, a matrix representation of the group G whose elements are E, A1, A2, AN, etc. Consider the sum H formed by multiplying the representation matrices H is equal to sigma, R is equal to 1 to N, DAR, D dagger, AR. Defined in this way, the product is Hermitian, that is S dagger is equal to H. HU is equal to SD, where SD is a diagonal matrix whose diagonal elements are real eigenvalues of H. We thus have the diagonal matrix HD is equal to U inverse sigma over R D of AR, D dagger AR of U, which can be written as U inverse D of AR into U inverse D dagger of U, and therefore HD written as a sum of D prime AR into D prime dagger AR, where D prime AR is obtained from DAR by the similarity transformation U prime D AR into U. Now, if we take the kth diagonal element of SD, then SDKK is the kth diagonal element of the matrix SD, which is from the above equation is D prime KJ AR, D prime dagger JK AR, which is equal to D prime KJ into D prime star KJ, which is equal to the sum over R of D prime KJ whole square. And which means that is a modulus square, it is greater than or equal to 0. And this can be 0 if and only if D prime Kj of AR is equal to 0 for all values of J, in which case the representation matrices are singular. Hence, dk is greater than 0. As a consequence, the diagonal Hermitian matrix SD is a non-singular Hermitian matrix. We can now define any power of SD, that is SD to the power m, can be defined whose kk elements are dk to the power m, where m is any real number, positive or negative. We can now define a square root of h by defining that h square is equal to the Hermitian matrix capital H, which of course is equal to h into h. S dagger is then equal to H, which implies that small h is equal to small h dagger. That is, the square root of the Hermitian matrix H is itself Hermitian. So the first result we require in order to define the square root is that the square root of the Hermitian matrix is itself Hermitian. Now let us define the new set of matrices D bar AR by similarity transformation with this matrix, which is square root of a matrix. That is, this new set of matrices D bar A are obtained by similarity transformation H prime DAR H for all R 1 to N. Now, D bar also form representations which are equivalent to the representation DR because they are obtained from similarity transformations. We will now demonstrate that D bar A is unitary. So, consider D bar A, D bar dagger A, D by itself H inverse DAR H, then D dagger is H dagger D dagger H1 inverse dagger, which can be manipulated slightly in a way that you can write this as H inverse sigma over S D of AR AS D dagger AR AS H inverse, where we have used the group multiplication, which is equal to H inverse D AM D dagger AM H inverse, again by using the group multiplication law, which is H inverse capital H inverse, which is equal to a unit matrix by the rearrangement theorem. Hence, the proof is complete. We will now discuss the representations and how to obtain them. Finding the irreducible representation of a group is one of the most important tasks, and this is not always easy. However, for finite groups, it is easy to derive the regular representation from the group multiplication table. And what is this regular representation? This regular representation contains all the irreducible representation of the group. How do we construct the regular representation? Consider the group G of elements E, A2, A3, AN and construct the multiplication table such that we have the identity element along the diagonal. Because this is a finite group, so every element has its inverse in the group itself. So we can multiplication table such that in the row we have the elements of the group E, A2, A3, A4, etc. And in the column, first column, we have the elements E, which is the inverse of E itself, the inverse of A2, inverse of A3, inverse of A4, and in this way we construct the multiplication table. So in this multiplication table, identity element is along the diagonal. Now obviously this can always be done because given any group, you can construct a multiplication table and by rearrangement theorem, you can rearrange your elements along a particular column or a row such that all the identity elements lie along the diagonal of this. Regular representation is defined, therefore, as the regular representation dr, which is defined as a matrix. So the ijth element of the regular representation of D corresponding to the element AR is equal to 1 if AI inverse AJ is equal to AR and is equal to 0 otherwise. Thus, for each group element AR, we have dr of AR is equal to 1 if the entry ij in the group multiplication table equals AR, otherwise dr of AR is equal to 0. We will now illustrate this with the help of an example. The example is to construct a regular representation of the cyclic group Z4, which consists of 4 elements E, A square and A cube, such that A4 is equal to E. the multiplication table is easy to construct. We have the table shown on the left-hand table of the slide, and from here you can see that inverse of A is A cube, inverse of A square is A square, and inverse of A cube is A, and inverse of E is equal to obviously E. We can rearrange the elements in such a way that the identity element occurs on the diagonals, such that instead of the first column being A square A cube, we write A cube A square A, and the new table that we form has the identity elements along the diagonal as 1, which is along the diagonal, and all the other elements equal to 0. So D1, D of E is as shown. Likewise, D of A, for example, is obtained by replacing the element in the matrix wherever A occurs by 1 and all other elements being 0. Matrix representation we obtained are shown in the slide, and from this one can easily verify by explicit matrix multiplication that, for example, dA cube into dA is equal to D of A4, which is D of E, is a diagonal matrix 1. We will now discuss the representations for geometric group transformations. There are many symmetry groups in physics which have transformations which are geometric in nature, like rotations. In these cases, group representation can be represented by operations in the coordinate space. As an example, consider the symmetry group D3 of the triangle. We have already seen that the symmetry group of the triangle consists of 6 operations, which are: number 1, the identity, which leaves everything unchanged; a clockwise rotation in the plane of the triangle designated as C3 by an amount 2 pi by 3; a clockwise rotation by 4 pi by 3 designated C3 square. Again, this rotation is in the plane of the triangle. Then we have reflection x represented by sigma v. Then the fifth symmetry operation is a rotoreflection. That is, first a rotation by 2 pi by 3, then followed by reflection, x goes to minus x, designated as sigma vx. Then we have the final symmetry operation, which is the rotoreflection, that is a rotation again by the same angle 2 pi by 3, but now followed by reflection, where y goes to minus y, represented as sigma. The transformation for the case where your geometric transformation can be obtained in the following way. For the purpose of illustration, we have considered a regular triangle with all its symmetry operations. Now, to obtain the group transformations, what we do is, instead of transforming the triangle, we keep the triangle fixed and rotate the coordinate axis counterclockwise, such that the elements of the symmetry group D3 be identified with this rotation. The rotation between the new coordinates x prime, y prime and the old coordinates x, y are given by x prime is equal to x cos theta plus y sin theta, and y prime is equal to minus x sin theta plus y cos theta, which can be written in the matrix notation that the transform coordinates x prime, y prime are given by this rotation matrix cos theta sin theta minus sin theta cos theta acting on x and y. Now the group elements can be generated by the matrix dA such that x prime is equal to dAx, where x is now a vector. Thus, it is easy to see matrix representation of the 6 operators, namely identity. The identity takes the xy back to xy, therefore theta is equal to 0, and therefore E, the element identity representation, is 1, 0, 0, 1, a diagonal matrix which is 2 by 2. C3 is a rotation by angle of 120 degrees, which means that theta being 120, cos theta is minus half, sin theta is minus root 3 by 2, and we obtain the representation of C3 in the form of 2 by 2 matrix, which is a rotation matrix, minus 1 half, root 3 by 2, minus root 3 by 2, and minus 1 half. So in this way, we can construct the matrix representation of all the symmetry operators. So students, let us summarize what we have learned so far in this module. What we have learned, number one, that a n by n matrix represented as D AI, if it satisfies the multiplication law of the group G, whose elements are AI, it forms an n-dimensional representation of the group G. And it is one of the most important representation, the matrix representation. Irreducible representation cannot be expressed as a direct sum of other representation, where if the representation is not irreducible like a regular representation, then it is a sum of all its representation, which always also contain the irreducible representation. Thirdly, irreducible representations are the building block of all other representation. Thus, all the other representation can be built once you have a list of all the irreducible representations. Every representation can be made unitary by suitable similarity transformation. So, if you have obtained a representation in the form of a matrix, then this representation can be easily made a unitary representation by a similarity transformation. And finally, for finite discrete groups, the number of irreducible representation is finite, and they are all contained in the regular representation. Thank you.